In part 1 of this lecture on detection probabilities, we learned how detection depended on distance to the animals. In this second part of the lecture, we'll take a recap on Mark-recapture concepts and learn how we can use these principles to estimate the detection function. As part of this lecture, we'll take a small recap on the capture-recapture concepts then, and learn how to use these concepts using an array of detectors. First, we'll start with a short recap on the Mark-recapture ideas. Imagine there's a population of capital N animals. We're interested in estimating how many animals are in the population. What is N? We usually cannot count or detect them all, so we will go out and count a sample, which we'll call little n. Little n is the number of animals we detected. In this lecture, I will use the words sampled and detected interchangeably. We know that we did not detect all the animals, so we need to work out how little n relates to big N. We need a way to estimate what proportion of the population we detected. This is what the parameter p is about. It can be thought of as the proportion of the population that we detected, or the probability of being included in the sample little n. We'll talk about how we can estimate this parameter with Mark-recapture next. Again, we start with a population of n animals. We're interested in estimating how many animals are in a population. What is n? Imagine our samples are taken by some kind of an animal detector. And detector 1 samples little n1 animals and marks these in some way. So what does marking mean? It simply means that you need to be able to identify those individuals that detector 1 sampled when they are sampled or detected again by a different detector, in this case detector 2. In this example, we add a red mark to the animals sampled by detector 1. There are other methods for marking. Lots of animals have natural markings that allow us to identify them to individuals. This cannot be done for individual gibbons or gibbon groups, of course, but we'll cover later on how we can mark gibbon groups. So little n1 represents the number of animals detected by detector 1. All these animals are marked now. These are then reintroduced into the population, and we have m1 marked animals in the population. As all animals detected by detector 1 are marked, m1 is the same as n1. And we know exactly how many animals are marked in the whole population. So imagine now that we have a second detector which samples n2 animals. And some of these, m2, are the same that were detected by detector 1, and others are new animals. You can see now that marking animals detected by detector 1 allows us to identify which of these animals detected by detector 2 were also detected by detector 1. So what information do we gain from these detectors or samples? We have a population of n animals, capital N, and this is unknown, and the quantity we're interested in. We know N1 and M1, the number of animals detected and marked by detector 1. We know N2, the number of animals detected by detector 2. And we know M2, the number of marked animals that were detected by detector 2. That's the number of animals that were recaptured. We're now going to use this information to create an intuitive estimator of P, the parameter, the probability of being detected. If N2 is a representative sample of the whole population, P is simply the proportion of marked animals in the second sample. In other words, P equals M2 divided by the number of marked animals in the population, which is M1. You can also ask what proportion of the marked animals are we recapturing with sample 2. You can think of it as detector 1 is setting up M1 trials in the population with sample 1. For each of these trials, there are 2 possible outcomes. Detector 2 will detect these animals as well, which makes those trials a success, or it will not, which makes the trial a failure. So the M2 recaptures in sample 2 represent the successes out of those trials, and the proportion of successes out of the trials gives you your probability of detection. Let's go back to this slide from part 1 of this lecture series and see how we can apply the Mark-recapture component here. The calls in this example are equivalent to the animals in the previous example. So here we pretended we would know that each animal produced 10 calls, and that for producing the gray histogram, all 10 calls from each animal were detected by all 16 detectors. In the context of what we just learned about Mark-recapture, we can say that we used these gray detections, the detections of all 10 calls, as the trials for each detector, and looked at the proportions that were actually detected by the detectors. So the black bars were the successes. We'll now look at what actually happens. Remember, we actually don't know how many calls each animal produced, and not all calls are detected by all detectors. So we don't really have the gray bars as shown here. Instead, some are detected by only one detector and others by 2 or 3 or more. We'll look at how we can use this principle from the previous slides to estimate the detection function with the 2 parameters shown on the left here. For that, we need to know how can we set up the trials, what trials are considered a success, what trials are considered a failure, and how do we incorporate distance into the Mark-recapture concept from the previous slide. We'll start with a simple example where we apply the Mark-recapture principle to 2 detectors and 10 animals. Here each animal the animals are represented by the green dots. Each animal was detected by one or the other detector. Some animals were detected by both. And the green lines indicate which detector detected which animal. Let's assume for now that we know the locations of the animals, and therefore we know the distances to the animals that were detected to both detectors, and not just the one that detected it. First, we look at it from the perspective of detector 1. We focus on 2 types of detections. Those detected by detector 1 and by detector 2, which are shown in blue now, and those detected by detector 2 and not by detector 1, which are shown in red now. We don't worry about the green detections now. They only represent those that were only detected by detector 1. So red and blue together represent the trials set up by detector 2, and we have 7 of those. Out of these, the blue ones represent the successes. We have 5 of them, and the red represent the failures, and we have 2 of these. We can do the same thing from the perspective of detector 2. Now it is detector 1 setting up the trials for detector 2. So those detected by detector 2 and by detector 1 are represented in blue, and those detected by detector 1 and not by detector 2 are shown in red now. And red and blue combined represent the trials, and blue represent the successes, and red the failures. So the green ones here represent those animals only detected by detector 2, which we don't worry about in this exercise. So we keep saying that we don't actually know where the animals are or what distances, what the distances are. And we'll get to where we obtain the information required for estimating the detection function later on. Well, what we do know is where the location of the detector is and how far the detectors are from each other. That is why we call this method spatial capture-recapture, or SCR for short. So this was a simple example with 2 detectors to illustrate what trial successes and failures are. And we saw this from the perspective of detector 1 and from for detector 2. We'll now look at a more complex example using 16 detectors and lots more detections. So now we go back to our example with 16 detectors, and in this example we have about 70 detected animals, 71 to be exact, and about 100 detections. So we'll do the same exercise as the 2 detector example, but this time we'll keep a tally of how many successes and failures we had in each distance bin for each detector. We use the Mark-recapture concept from the previous slides to estimate the detection function. Let's begin with detector 1. This is a zoom into the area surrounding this detector, which allows us to focus on the nearest 600 meters around it. So we focus on 2 types of detections now. Those detected by detector 1 and by another detector, and this can be any other detector. These are shown in blue. And those detected by another detector and not by detector 1. These are shown in red. So any detector can set up trials for any other detector, in this case for detector 1. Red and blue together represent the trials that are set up. But notice this time we don't draw the dashed lines in as before because the plots would get too busy. So we can start building our histogram of trials, successes, and failures now. So now the total bar height, combining the blue and red, represents the trials in each distance bin, and the blue sections of the bars represent the successes, and the red sections represent the failures. We limit this exercise to 600 meters from the detectors, so in this case from detector 1, as almost no detections were made past 600 meters. So we would barely have any successes past 600 meters, pretty much only failures. So looking at this from the perspective of detector 1, we have 3 successes, 2 within the 3rd distance bin and 1 in the 4th distance bin. Next, we'll look at it for detector 2. And again, we have 3 successes, 1 in the 1st distance bin, 1 in the 3rd distance bin, and 1 in the 4th. We have several more trials that were failures, marked by the red dots. And so we can add these to the histogram on the right. For detector 3, we only had trials that were failures. So we only increased the red bars in the histogram. Similar for detector 4, we only had trials that were failures. So we only increased the red bars in the histogram. As a side note, you might wonder what happens to the 5 detections made by detector 4 and no other detectors. Are we not going to use these detections? It seems like they're not counting towards the bar heights on the right, but that's not correct. They're counting in that they represent trials for other detectors. So we keep doing this for each of the detectors and keep adding the successes in failures to the histogram. And finally, eventually, we will end up with a distribution of observed successes and failures, just like our black and gray histogram from before. So now we can go ahead and plot the proportion of successes within each distance bin in blue versus the red failures in a proportion plot, shown here on the left. So in the first distance bin, for example, we only had successes, hence the proportion of successes was 1 in the first distance bin. In the second distance bin, we had 9 successes and 3 failures. So the proportion of successes was 9 out of 12, which is 0.75, and so on. This way we obtain the shape of the detection function and are able to estimate the parameters G0 and sigma. So here are some key points to take away from this lecture. We can detect and mark and recapture marked animals by different detectors. We can use recaptures of marked animals to estimate the proportion of the population sampled. Spatial locations of where the animals were captured and recaptured provides information on where the animals are. And detectors can set up trials, mark animals, for other detectors at different distances to the detectors. The proportion of recaptures at different distances provides information about how detection probabilities decrease with increasing distance from the detector. In the next lecture, we're going to look at how we can use the number of detections and the estimated detection probabilities to estimate animal density or animal abundance.